Hello everyone, my name is Geiger and I'm a second year mechanical engineering and physics student in Bilkent University. Today I'm going to present our project, which is designing a computer assisted Geiger counter system to analyze half-life of materials. In this part I will explain the theoretical part of the experiment and I will talk about the procedure, how we did things in this experiment, and later we will move on the real experimentation part. So first of all, we have a specimen, radioactive specimen, that emits beta particles. And these beta particles are captured via our Geiger tube. As you know, Geiger counter has argon in it, and argon is an inert gas. Therefore, it's easy to rip out electrons from argon. And these high energy beta particles can do that actually. And when they do that, those electrons also rip out other electrons from other atoms. Therefore, we can capture an electrical pulse from the Geiger tube because of these emitted beta particles. And to capture these data, we need high voltage here, and that is supplied by our amplifier. Later on, you will see the amplifier in our circuit. Moreover, this pulse is detected by a pulse detector, and you will also see the pulse detector in the experimentation part. And the pulses are captured by Arduino microcontroller unit, and then it's transferred to MATLAB, to computer, to gather data. For now, we are currently experimenting on strontium-90 element, and we are expected to see this exponential decay in the long run. But however, we cannot see that because strontium has a half-life of almost 30 years, and it's hard to capture. Therefore, we are currently on this part. But in a previous measurement, another group found the same exact specimens count per minute rate as 1,450, and we are now finding this value approximately 1,350, and we can plot this exponential decay from there, and that's the general concept of this experiment. So this is the setup of our physics project. This is the circuit that we created using certain oscillator integrated circuits, and this is the specimen. This is the Geiger tube. If you look closely, you can see the Tozens avalanche phenomenon occurring here. This is the high voltage that we drive the Geiger tube with, and for convenience, we also look for the data in oscilloscope. This is the raw data captured by the oscilloscope here, and this is the shifting data that we capture via Arduino microcontroller, as we can see here. So this basically captures the peaks of our specimen and plots it over time. As you can see, we have measuring this specimen for almost 2 hours. It kind of converges to some number here. If we can average this, we can get the count rate for this orientation. The orientation in this figure. And the data here is for a different orientation. We first started counting, but considered that the values are quite low. We switched to another configuration, as you can see here. And this is the filter sensor data. As a result of this experiment, we found that the half-life of strontium-90 element is 29.34 years. On the other hand, half-life of the material, which is strontium-90, is specified as 28.7 years in its label. The error in this measurement is 2.2%, but there are some reasons for it. For example, radiation is not a fully determined event. There are some randomness in it. and we cannot exactly determine the direction in which the particles go after they are generated. Therefore, there occur some fluctuations in our measurement, as you can see in the count per minute plot. In order to decrease the error, the longer measurements can be taken. And also due to the time scale of the half-life of materials that we used in this experiment, we could not determine the half-life by the system itself. But for longer or more distributed measurements for this exact specimen, or measurements with quite small half-lives can be taken in order to display the exponential decay and predict the half-life of materials.